Okay, Bismillahirrahmanirrahim. Wassalatu wassalamu ala Rasulillah. So we will solve recitation problem for chapter 23. And let's begin. So the first problem reads, two long fin rods with linear charge density, lambda 1, so this is my first linear charge density, 6.5 nanocoulomb per meter, and lambda 2 is minus 3.5 nanocoulomb per meter. So these two long fin rods with these linear charge densities, they lie parallel to each other and are separated by a distance of 15 centimeters, okay, as shown in the figure below. So you see this is the first rod and I gave you lambda 1. This is the second rod and I gave you lambda 2. Of course, lambda 1 is positive and lambda 2 is negative. So the question is, determine the position of the point along the x-axis where the net electric field due to the two rods is 0. Okay, so I want the position of the point at which E total, basically the net electric field created by these two charge rods, is equal to 0. So let me give you the x-axis. This is the x-axis, as you can see. Of course, it goes this way. This is the x-axis. Okay. So what did we study about a rod? If I have a rod and I give you the linear charge density of the rod, the electric field E is lambda divided by 2 pi epsilon naught r. Okay. This is an electric field, the electric field created by a rod of linear charge density lambda at a distance r. So if you remember, of course, my K is 1 over 4 pi epsilon naught. So that means here, this is just 2 times K. By the way, K is 10 to the power 9 SI units, of course. So 2K multiplied by lambda divided by R. Okay, so this is in your formula sheet. And this is just another expression of the same thing. I just replace this 1 divided by 2 pi epsilon by 2K. Yeah. Okay, good. Now, of course, if I have a charge rod with linear charge density, if lambda 1 is positive, of course, it's pointing away, okay, radially outward, okay? And at the distance r, I already gave you what's the electric field, is 2k lambda divided by r, or lambda divided by 2 pi epsilon naught r. Good. If, of course, the charge density is negative, like lambda 2, it's radially inward, okay? Pointing toward the negative charge, okay? It's pointing towards the rod, okay? But the electric field, of course, will give you the same type of thing. So here I will have E1, this is lambda 1, here I will have E2, 2K, lambda 2 divided by R. Now this is just a reminder, okay? And how we got it, you remember we got it using Gauss law. So I'll come back to this later. Now let's come now to our problem and solve it. So these are my two rods. Okay, let me just do it this way. So this is lambda 1, and this is lambda 2. And this is my x-axis. So my origin is right here in the middle. And of course, this lambda 2 is at plus 7.5. We'll put it in meters later. And with respect to the origin, you see the origin is here right in the middle. So here is just at minus 7.5 centimeters. Okay, now let's draw the electric fields. Let's say for lambda 1, of course, lambda 1 is positive. So the electric field here in the middle is pointing away towards my positive x direction. Here, of course, this is pointing toward my positive x direction, and here is pointing along my negative x direction. Okay, this is E1. And of course, it's inversely proportional to the distance. Now, let me do it this way. For E2, the electric field created by the rod negatively charged, the negatively charged rod, lambda 2 is negative. Okay, so it's pointing towards it. So of course, E2 here is pointing towards this rod here, which is negatively charged, and here it's pointing towards it, which is negatively charged, and here it's pointing towards it because it's negatively charged. So now let's come back to the question. What is the position of the point along which or at which the net electric field is 0? Of course, here, this is E1, this is E2. Here, they cannot be equal to 0. Why? Because here, of course, E1 in magnitude is always bigger than E2 in magnitude. Because I'm closer to, of course, the rod number 1, that's number 1. But also, this lambda is bigger, okay? So you see here, for E1, this lambda 1 is bigger, but also this R is smaller. So overall, my E1, the magnitude of the electric field is bigger than E2. Okay, the magnitude of the electric field created by the positively charged rod will be always bigger than the magnitude of the electric field created by the negatively charged rod. So here, no, I cannot have net electric field is 0. I cannot have it. Okay. Okay. Good. Here I cannot have it as well. Why? Because they are pointing along the same direction. So net electric field here is different from 0. Here now I can have net electric field is equal to 0. Okay. So here, yes, net electric field, E net, which is just E1 plus E2, it can be equal to 0. So now let's find it. Let's find the position at which the electric field is equal to 0, because you see they are pointing along a different direction, of course. So E net here will be just plus E1 minus E2. Okay, I have projected along the positive x direction. Okay, they are pointing along different direction, and the magnitude can be equal, and this should be equal to 0. So that means E1 in magnitude can be equal to E2 in magnitude. Now, what is E1 in magnitude? E1 in magnitude will be 2 times, it's an infinitely long rod. Okay, so the electric field is 2 times K lambda 1 divided by the distance. Now the distance here, let me call here x. So the point I'm looking at which the electric field is 0 is x. Okay, so here I have net electric field is equal to 0. Now I'm looking, I want the distance between this x and the positively charged rod. Of course, x is from the origin, right? So this is x. Okay, I have to add this distance here. So I will have 2k lambda 1 divided by the distance, and the distance will be x plus 0.075. Okay, and this should be equal to 2k lambda 2, I'm talking about in absolute value, of course, right? Because I'm talking about magnitude here, divided by the distance between x and the negatively charged rod. And that's just x minus 0.075. Okay. So you see 2k will be simplified, and I will have basically lambda 1 in absolute value, which is 6.5 10 to the power minus 9 coulomb per meter, and lambda 2, which is absolute value, of course, 3.5 10 to the power minus 9 nanocoulomb per meter, coulomb per meter. Of course, the 10 to the power minus 9 will simplify, and I will have this equation here, which is 6.5 times x minus 0.075, and this should be equal to what? 3.5 times x plus 0.075. Let me solve this problem. If I solve it, of course, you know how to solve this equation. I'll get an X, which is equal to 0.25 meters, which is X is equal to 25 centimeters. So at X here, so 0 is here, this is 7.5. At X here, which is 25 centimeters, I will have net electric field due to these two infinitely long rods. Net electric field here will be 0. E1 plus E2 will be 0 at 25 centimeters. Okay, is it clear? Good. Now, what do I want you to remember? I want you to remember that electric field created by a rod which is, infinitely long and which has a linear charge density, the electric field is just E1, 2, is just lambda 1, 2. Okay, of course, absolute value divided by 2 pi epsilon naught r, r being the distance between the point I'm looking at and the rod. Okay, and this I can write it as E1 or 2 here will be just 2k lambda 1, 2 divided by r. Okay, just by using this. Okay. And of course, I have here principle of superposition. So is it clear? Okay, now let me go to the next problem here. And exactly that's what I did here. Okay, and you see, I find it. Okay, so you can do it again. And you find the answer here. Now let's go to this problem here. Let's read it very carefully. What do we have? So the figure shows a portion of two large parallel, okay? You highlight this large parallel non-conducting sheet, placed 4 centimeters apart and carrying uniform charge densities of sigma 1 and sigma 2. You see, these plates here are large, parallel, and non-conducting. Okay, and the distance between them is 4 centimeters, 0.04 meters. And they have both, let's say, uniform charge density, sigma 1 for the first one and sigma 2 for the second one. Now the electric field between the sheets has a magnitude of 1.45 10 to the power 5 Newton per Coulomb. So this electric field here, as you can see, is directed to the left, and it has a magnitude of 1.45 10 to the power 5 Newton per Coulomb. Now, if sigma 1 is positive and is equal to 6.5 microcoulomb per meter square, find sigma 2. So I know that sigma 1 is positive. Okay, the value of sigma 1 is given here. Now the question is, what is sigma 2? Such that the electric field between these two plates, large parallel non-conducting plate, is 1.45 10 to the power 5 Newton per Coulomb. Okay, great. So I know sigma 1 and I know the plate is non-conducting. Well, I know that the electric field created by a non-conducting plate that has a uniform charge density of sigma 1, E1 is just sigma 1 divided by 2 epsilon naught. If it was conducting, it would be sigma divided by epsilon naught. Non-conducting electric field is sigma divided by 2 epsilon naught. So I can really calculate what the electric field created by sigma 1, the large non-conducting plate of charge density sigma 1. So I know sigma 1, 6.5, 10 to the power, it's microcoulomb, right? So 10 to the power minus 6 coulomb per meter square divided by 2 times, what is epsilon? 8.85, 10 to the power minus 12 with the right SI units. And you do the calculation, how much do you get? So the electric field is, due to this first plate here, is 3.67, 10 to the power 5 Newton per Coulomb. and this is E1. Okay, so sigma 1 is positive. Of course, I know the magnitude of the electric field, and you see it does not depend on the position. Okay, this is a constant, of course, in the vicinity of my plate. And of course, sigma 1 is positive. That means it's pointing away, normally, radially away from sigma 1. Okay, so that means that my E1 is pointing in this direction. It's pointing in this direction. Of course, the magnitude is the same. It's pointing away. This is E1. The magnitude is the same, as you can see. The direction is away from my positively charged non-conducting sheet. And again, magnitude of E1 here is 3.67 10 to the power 5 Newton per Coulomb. Good. Now, what do you think? What should be sigma 2? Sigma 2, should it be positive or negative? Sigma 2 should be positive. Okay, that's number 1. Okay, and not only it's positive, but it has to be larger in absolute value. So sigma 2 has to be larger than sigma 1. Why? Because now you know that the electric field is always pointing toward the lower potential, right? So in reality, sigma 2 should be larger than sigma 1. And both are positive, right? If sigma 2 was negative, of course, the net electric field will be pointing toward the right. Okay, so sigma 2 is not only positive, but I know that in magnitude, sigma 2 should be larger than sigma 1. Now, let me take another color for sigma 2. Okay, let me take another color for sigma 2. So sigma 2 is positive. Of course, will be pointing away. So this is E2. And of course, E2 will be pointing in this direction. This is E2. And E2 will be pointing in this direction. Okay, it's larger than E1. Okay, good. Now, here what I'm looking at is in between. Let me call it the middle. Let me call this part 1. I don't want to study part 1. And this part, I call it part 2. And in between, I call it capital M. Now, when I'm in the middle, my net electric field, principle of superposition, is equal to E1 plus E2. Electric field created by plate 1 plus electric field created by plate 2. Now, let me choose a positive x-axis. This is my positive x-axis. It's pointing towards the right. Now let me project this vector along x-axis. E net, well, I know that E net is pointing along negative x-axis. So this is minus E net. E1 is pointing toward positive, so it's plus E1, right? E2, of course, E2 is pointing along negative, so minus E2. So that means my E2 will be just equal to E1 plus E net. So E1, I already calculated it. What is E1? 3.67 10 to the power 5. It's just this number here, sigma 1 divided by 2 epsilon naught. What is E net? E net is given by the problem. You know, the electric field between the sheets has a magnitude of 1.45 10 to the power 5. So I add 1.45 10 to the power 5. And this should be equal to E2. But remember, E2, of course, will be equal to sigma 2 divided by 2 times epsilon naught. So now I know my sigma 2. Okay, sigma 2 will be just this number here. And I multiply by 2 epsilon naught. And I calculate it, of course, I will get 9.07 10 to the power minus 6 Coulomb per meter square. So this gives you 9.07 microcoulomb per meter square, and this is the right answer here. Okay, so be very careful. Okay, now we solve the problem. Okay, and you got your full mark, but don't stop here. Look at the problem and you ask your question ask yourself different questions. You see, if sigma 1 is positive, and sigma 2 is negative, you see, in the middle here, the electric field, so if sigma 1 is positive and sigma 2 is negative, the middle, the electric field, so this is E1, it's pointing away, and here E2 will be pointing towards. So this is E2. The net electric field here will be larger. E net in between these two plates will be just E1 plus E2. You see, because they are pointing in the same direction. And you see, sigma 1 is positive and sigma 2 is negative. And you see my electric field is pointing towards lower potential. Now you study potential in chapter 24. Okay? But even if you don't know that, you know that principle of superposition is telling you that the E net here in the middle will be larger because it's a sum of two vectors going in the same direction. Okay? Now, whenever I have two plates, now the net electric field in between is less than one of these electric fields. That means that these two have the same sign. Okay. So here's the net electric field here in this problem. You see, the net electric field is 1.5 10 to the power 5. E1 is just 3.7. That means E2 will be reducing the effect of E1. So E2 will be opposite of E1. And this is exactly what we found here. Sigma 1 is positive and sigma 2 is positive. And moreover, sigma 2 is larger than sigma 1. And you see, this is what I have. And I get my sigma 2, you see, it's larger than sigma 1. Okay. Now, I could have asked you a question about the electric field here, the electric field here. Well, we already solved that in class. Now, let me go to the next question. So the next question reads, we have a particle, and I give you the charge of the particle, 26 microcoulomb, and it's placed at the center of a spherical shell of outer radius 22 centimeters. Let me draw, okay? So I have a spherical shell. So this is the inner radius of my spherical shell, and this is the outer radius of my spherical shell. And at the center here, I have a charge, let me call it Q, and Q is equal to 26 microcoulomb. Okay, good. Now what's the question? The question is, what is the electric flux through half of the shell surface? So here I gave you this distance, okay? The outer radius is just 22 centimeters. Now I'm asking you to calculate the electric flux through half of the shell surface. Okay, easy. I will apply Gauss law. Okay. The flux is just integral over my closed surface of E dot dA. And this is the flux of electric field, electric flux. And electric flux is equal to charge enclosed divided by epsilon naught. Okay, good. But again, this is the flux through the whole shell. Here, what I want is I want the flux through half of the shell. Okay? So basically, I want half of the flux. I want half of this electric flux. So that means I need just to get the charge enclosed divided by half multiplied by epsilon naught. Okay? This is basically, you know, this is the full shell. I don't want the flux through the whole shell. I just want the flux through half of the shell. Okay, this is the half of the shell. It's passing through a diameter. Okay, this is the first half of the shell, and this is the second half of the shell. I just want the flux here. So this flux is half of the total flux. So half of charge enclosed divided by epsilon naught. Now, what is a charge enclosed? Well, easy. Okay, let me just, you know, my Gaussian surface is here. Of course, the whole shell is my Gaussian surface. So charge enclosed is just this Q naught, this Q here, which is 26 microcoulomb, so 10 to the power minus 6. Okay. Now I divide it by 2 times epsilon naught, which is 8.85 10 to the power minus 12 SI units. If you do that, how much do you get? Let me do the calculation. I get 1.47 10 to the power 6. Okay. And what is the unit of flux? Of course, it's Newton per coulomb multiplied by area meter squared. And this is half. Okay. Basically, this is the electric flux through half of the shell. Okay. This is, let's say, the top half. This is the first half. And this is the second half here. So of course, total electric flux through my whole shell will be 2 times this. And 2 times this. Okay. Clear? Good. Okay. So again, here my Gaussian surface is just my outer shell, right? Good. Let's go to the next question. Let me erase this first. Now, we have a positively charged particle Q, which is equal to 12 nanocoulomb, and it's located at a distance 5 centimeters from a center of an uncharged, thin, conducting spherical shell of radius 10 centimeters. Let me draw, just for the sake of things. So I have a positively charged particle located at this distance from a center of an thin, uncharged, conducting spherical shell of radius 10 centimeters. Okay, good. Now, this is my thin spherical shell of radius 10 centimeters. So this distance here is the radius, and it's equal to 0.1 meters. And here, this is the center, but at 5 centimeters from the center, let's say here, in the middle here, I put my charge capital Q, which is positive, by the way, and it's equal to plus 12 nanocoulomb. Okay, good. Now the question is what? Again, you highlight this, it's uncharged. That means on my spherical shell, Q is equal to 0. Let me write it small, Q is equal to 0 because it's uncharged. It's conducting and it's a spherical shell. Now the question is, find the magnitude of the electric field just outside the surface of the shell. Find the electric field just here, outside here. So how can we solve this? We will use Gaussian theorem. Gauss law, sorry. Gauss law is telling you that integral over my closed surface, of course my closed surface will be just this surface here, the outer surface of my spherical shell, because that's where I want to calculate my electric field, and of course it's a sphere. Integral over this Gaussian surface here of E dot dA, this is equal to charge enclosed divided by epsilon naught. Okay. Now, integral of E dot dA, of course, E here will be constant. So I can get it out of the integral. I will have E. By the way, here, of course, E is pointing in this direction because the Q inside is positive, and dA also is pointing along the same direction. Okay. So basically, E dot dA will just give you EA. So I can remove the vectors because cosine 0 is 1. So I have E, integral of the area. Of course, the integral of the area will be 4 pi r square, but here r is equal to the radius because I'm looking at just outside my surface of the shell. So it's just radius square. This is equal to charge enclosed. What is the charge enclosed? Of course, my thin spherical shell is uncharged. So charge there is 0. Now the only charge enclosed is just capital Q. It's just plus Q divided by epsilon naught, meaning that my E is just plus Q divided by 4 pi epsilon naught r square. So this, we already know this, by the way. This is just K, Q divided by r square. Let me put the numbers, 9, 10 to the power 9. Q is equal to 12 nanocoulomb, so 10 to the power minus 9. And I divide by the radius square, which is 0.1 square. If you do this, how much do you get? Of course, this goes away. And I will get something like 10,800 Newton per Coulomb. Okay, this is what I have. So in two significant figures, you will just get, let's say, 11,000 Newton per Coulomb. So this is the right answer. Okay. Of course, here it should be 11. So it's a mistake. Kilonewton per Coulomb. Clear? Next. Now let's solve this problem here, which is very important. So let's read the problem. We have the axis of a long, this is very important, okay? You highlight it. Long hollow metallic cylinder of inner radius 1 centimeter and outer radius 2 centimeters coincides with a long wire. This is also very important. Okay. So the wire has a linear charge density of -8 nanocoulomb per meter. Okay, linear charge density, lambda. And the cylinder has a net charge per unit length of -4 nanocoulomb per meter. And the question is, determine the magnitude of the electric field 3 centimeters from the axis of the cylinder. So here, let's draw a graph. So I have what? I have a hollow metallic cylinder. The cylinder, okay? Let's say this is R inner, basically 1 centimeter. And this is R out. And R out is equal to 2 centimeters. Okay. Okay, let me just draw this very quickly. And it's very long, meaning it's infinite. Okay. Okay, so this is very long, infinite. It's going up, up, down, down. So the axis is here. And on this axis, there is a long wire. And the wire has a linear charge density lambda wire, which is equal to -8 nanocoulomb per meter. And this long hollow metallic cylinder has a linear charge density, okay, a net charge per unit length of -4. So basically I'm giving you here the linear charge density of my cylinder. Let me write it. Lambda still is -4 nanocoulomb per meter. And the question is to determine the magnitude of the electric field 3 centimeters from the axis of the cylinder. Let's say 3 centimeters is somewhere here. Okay, this distance is 3 centimeters. And what is E here? Good. So E here will be simple. Now, I will solve it simply, and then I will give you the bigger perspective. Okay, good. Now let's look at it this way. First thing first, this has its importance. If I say a long wire, you know that the electric field created by this wire is just lambda wire divided by 2 pi epsilon naught r, and r being 3 centimeters, right? And this is the electric field created by the wire. In other words, this is just 2k lambda wire divided by r. I know k, I know lambda wire, and I know r. I can calculate the electric field created by the wire. Of course, it's negative, so it will be pointing inward, right? Radially inward. Now, for my cylinder, it's a hollow metallic cylinder, and it's long. This has its importance. By long, I mean I can consider it as a wire as well. So this long, hollow metallic cylinder, which is very long, can be considered as a wire, okay, like shell ferrite. Okay. Basically, I can consider it as a wire, a long wire, whose linear charge density is located in the axis, and I'm looking at the electric field at a distance r. So E cylinder is just lambda cylinder divided by 2 pi epsilon naught r. So that means this is just 2k lambda cylinder divided by r. And the electric field, the total electric field, of course, will be the sum of these two electric fields. And both of them, by the way, are negative because they are pointing radially inward. So this is E wire, and of course, E cylinder will be also pointing inward, right? But in magnitude, of course, I will take the magnitude. So I'll have just 2k lambda wire, by lambda wire, I mean absolute value, plus absolute value of lambda cylinder divided by 2 times r. So I will have 2 times 8.99 10 to the power 9. This is my k. Lambda wire. What is lambda wire? I know it. 8 minus 8. Of course, I take plus 8 because I want absolute value. I know the minus is already embedded in the direction. So I have 8 times 10 to the power minus 9 plus, of course, 4 times 10 to the power minus 9, because I have nanocoulomb per meter, divided by 2 times r. R is equal to 3 centimeters, and this will be 0.03 meters. And you calculate this, how much do you get? Of course, you get 7.2 10 to the power 3 Newton per coulomb. Okay, so the idea is here, my very long hollow metallic cylinder can be considered as the wire. Okay, focused, of course, at the center of the cylinder, and which has a linear charge density which is -4 nanocoulomb per meter. Okay, and we solve the problem. Now, let's be more fundamental. Okay, being more fundamental means let's apply Gauss law and make sure that we have what we want. And this will raise new question, but it will deepen your understanding. So this is my inner radius, and this is my outer radius. And this is what? Okay, and it's infinitely long along this direction. It's going very, very far up and down as well. Okay, it's very long, yeah. Infinite. That's why I'm talking about a long line. Okay, now let's apply Gauss law. I want the electric field here at a distance r, which is 3 centimeters. Okay, now here at the axis also, I have my wire. Let me just draw the wire. This is the wire. Okay, and I give you lambda wire, but here I give you what? I did not give you the surface charge density, I give you lambda. So let's call it lambda cylinder. Okay, let me apply Gauss law. Of course, I'll be choosing my Gaussian surface, which will be a cylinder located here. Let me draw it with another color. Hopefully you see what I'm drawing, okay? So let me draw my Gaussian surface with another color here. This is my Gaussian surface. And let me do it this way. Okay, it's a cylinder that has a radius R. Okay, this is my Gaussian surface. Let me apply Gauss law on this Gaussian surface. I will have integral over my closed Gaussian surface of E dot dA. This will be equal to charge enclosed divided by epsilon naught. Okay, good. Now let's do it. Of course, here the electric field is radial. Okay, so that means here on top here, my cap of my cylinder, and down here, well, dA are pointing this direction. So E dot dA is 0. Flux here is 0. And flux here is 0. So the only flux which is remaining is the flux here. Of course, this is my dA, and my electric field is pointing inward, right? Okay. Why? Because I have these dash fields which are negative. So E is inward. So this will give me minus E, which is constant. I put it out. Integral of dA will give me the area. But of course, it will be the lateral area. The lateral area, let me write it, area of the cylinder, meaning the area of the cylinder here. This is what I want. This is my Gaussian surface. Okay, and this will be equal to what? Of course, here I will have charge enclosed. So what is a charge enclosed? I have the charge enclosed from the wire, by the way. So if this Gaussian has a height, let's say, or a length L, okay, it's a height L. So what is a charge enclosed? I have charge enclosed. I have two types. I have charge enclosed, of course, wire, plus charge enclosed cylinder. And this divided by epsilon naught. By the way, the charge enclosed will be negative because both densities are negative, right? Okay, I can take absolute value if I want and get rid of this minus here. Okay, and I will be talking about E as absolute value, so as a magnitude. So let me put a plus here, and I put absolute value here and absolute value here, just to make sure that I get rid of the minus sign. So I will have E multiplied by the lateral area. Now, what's the lateral area? The lateral area will be 2 pi multiplied by radius of my Gaussian cylinder multiplied by L. Okay, L being this length here. And this will be equal to what? Charge enclosed by the wire. So charge enclosed in the wire is just lambda, the linear charge density of the wire, multiplied by L. Okay, this is the charge which is here, enclosed by the Gaussian surface, so it has the same length L. So the total charge will be just lambda wire multiplied by L. Of course, lambda wire, I mean absolute value of lambda wire. Now, what's the charge enclosed by the cylinder? So what do you think? What is the charge enclosed by the cylinder? The charge enclosed by the cylinder is lambda cylinder multiplied by L also. And this divided by epsilon naught. And you see my L goes away. And I have E, which is just lambda wire plus lambda cylinder divided by 2 pi epsilon naught divided by R, of course, which is just 2k lambda wire plus lambda cylinder divided by R. And this gives you the same answer. Okay. Good. Now somebody Some students who are very curious, they will tell me, but the charge enclosed here for this, the charge on the cylinder is lambda cylinder multiplied by L. But over my whole Gaussian surface, over my, let's say, whole long, hollow metallic cylinder, it's a surface. Well, I will tell them that this is the total charge enclosed. Here I give you lambda cylinder. You remember, total charge is just charge density multiplied by the volume, if I have a volume, okay? And it's equal also to surface charge density multiplied by the area, if I have a surface charge density, but it's also equal to lambda, which is a linear charge density multiplied by the length. Okay. So here, my cylinder, I describe it as linear charge density. So basically what I mean here is the total charge is just lambda multiplied by L. By L, I mean the, along this length here, L, this is L. If instead of giving you this, I gave you sigma. Instead of giving you this, I tell you, oh, this hollow metallic cylinder has a surface charge density of sigma. That means if I want my total charge, which is enclosed by the Gaussian surface, it will be sigma multiplied by the area of the hollow cylinder. Of course, I'm talking about the outer surface. Okay. So it will be, what is the area? So if I gave you sigma instead of lambda here, I have to multiply by the area of the outer surface of my cylinder, which is 2 pi multiplied by R outer, which is 2 centimeters, multiplied by the length L. Okay. But here I did not describe it using sigma. I describe it using lambda. So this should be lambda, which is my net linear charge density, net charge per unit length, multiplied by L. Okay. So this gives you a relationship between sigma and L and lambda. Okay. That means basically that my sigma in this specific case of having a cylinder is just lambda. So because the LL goes away, divided by 2 pi R naught. Okay. So I can say that the charge enclosed by the cylinder here will be what? Will be sigma multiplied by the area. But what's the area? Of course, the area will be 2 pi R out L. But remember here, sigma here is just lambda divided by 2 pi R naught. You see the 2 pi R naught goes away, and I just end up with sigma, basically lambda cylinder multiplied by L. You get my point? Okay, this will come again. Okay, so just be aware of this type of relationship. I can describe the total charge either by giving you the volume charge density or giving you the the surface charge density, or by giving you the linear charge density. But you know that I can, use this relationship to get the relationship between sigma and rho and of course lambda. Okay, it depends of course on the geometry that I'm looking at. And here the relationship between sigma and lambda is sigma is equal to lambda divided by 2 pi R outer, because that's the surface that I'm looking at. Anyway, I'll come back to this later. Okay? Bottom line, this long hollow metallic cylinder can be considered as infinite, and it can be considered as a rod. It behaves like a rod, like a wire, okay, a one-dimensional object. Okay, so my net electric field is just 2K lambda, let's say wire, plus lambda cylinder that I gave you divided by R, which is 3 centimeters. Okay, good. And of course, here this lambda, I mean absolute value, okay, because I know that it's radially inward. Next question. So let me erase this and then we go to the next question. And this is what I did here, okay? But this does not do justice to, the problem, that's why I want you to see how to solve it using this E dot dA. Okay, this is why I wanted you to see it. Okay, so this is a shortcut. If you understand what's going on, you can use it, of course, but always you can come back to the fundamentals. Good. Now let's solve this problem here. Read it carefully, and then we go very. So in this previous problem, let me say it, you can think about what should be the electric field inside, outside. Okay. So draw me the electric field line inside and outside. Okay, this is my Y. Let's say this is a top view. Okay, this is my Y. It's negatively charged. Lambda Y is negative. Of course, the electric field will be pointing towards it, radially inward. Okay. And then here I have a hollow metallic shell. This is the top view. I'm looking from top. Of course, since here it's negative, what do you think? Of course, here it will be kind of positively charged. Okay. And here, of course, it will be negatively charged. I will come back to this later. And you see how the electric field will look like. Of course, inside my metallic cylinder, the electric field is 0. Okay. So electric field is going from positive to negative. That's why here it's radially inward. Here is 0. And of course, here it will be outward. And it will be radially inward, sorry, on the outside. Okay. And here what I did was at 3 centimeters here, what was the electric field? And that's what I calculated here. Of course, it's radially inward, and I have to use a kind of shelf area. Okay. So the electric field is just the electric field due to the wire, plus the electric field due to my hollow metallic cylinder focused in the middle, okay, at the axis. So it looks like I have 2 wires effectively because my cylinder behave like a line charge, behave like a wire basically. Okay, now let's go to this problem here and let's read it very carefully. What do we have? We have a spherical conducting shell that has a net charge of 12 10 to the power minus 6 Coulomb. Now, if a point charge Q of minus 5 10 to the power minus 6 Coulomb is placed inside the spherical shell, find the charge on the inside and on the outside of the surfaces of the conducting shell respectively. Okay, let's draw. So this is my spherical shell. Let's say this is inside and this is the outer surface. Okay, and this shell has a net charge, let me call it Q net, which is 12 10 to the power minus 6 Coulomb. And it's positive, of course. Now I take this point charge here, Q, and I put it here, inside, everywhere. Let's say, let me put it here. Okay. And Q, of course, let me call it Q1, is minus 5 microcoulomb. Now the question is, what is the charge here on the inner surface and on the outer surface? Of course, this is a spherical conducting shell. It's conducting. So that means I can have induced charge, and the net charge was 12. You guess what will happen, right? So here, I'll be having this. So here, of course, I have electrostatic equilibrium. Electrostatic equilibrium, which is the case everywhere in this chapter. I have electrostatic equilibrium here, okay? So if I have electrostatic equilibrium, that means the electric field here inside is 0, of course. I can use a Gauss law. Let me take this Gaussian surface, and I can use a Gauss law. If I use the Gauss law, well, the flux, which is an integral over this closed surface of E dot dA, but E itself is 0, so the flux is 0. And this is charge enclosed divided by epsilon naught. Now, what's the charge enclosed by this surface here? Of course, the charge enclosed will be Q1 plus Q inside. By inside, I mean the charge all around my inner surface. And this should be 0. So that means the charge inside, of course, will be minus Q1. Okay? So Q1 was 5 microcoulomb, so charge inside will be plus 5 microcoulomb. So this is my charge inside. So 5 10 to the power minus 6 plus 5 10 to the power minus 6 microcoulomb, just by Gauss law. Okay. So I have used Gauss law. Now, next thing I will use is conservation of charge. You see, in my conducting spherical shell, Q net was equal to plus 12 10 to the power minus 6 coulomb. Okay. So this should be conserved. Okay. So this is equal to charge inside plus charge outside, because I know that there is no charge in between. Okay. So I have charge on the outer surface and charge in an inner surface here. And again, the charge in the inner surface is due to what? Is due to this Q1. Okay. If I did not have Q1, I will not have charge in the inner surface. But because I have Q1, I will have induced net charge in my inner surface. Okay. If I did not have charge Q1, you know that inside a cavity, there is no charge in the inner surface. All the charge will be on the outer surface. Now, charge inside, I already know it. So this is just plus 5 10 to the power minus 6 coulomb. And this is charge outside. So that means that my charge outside will be just 12 minus 5 10 to the power minus 6 coulomb, which is plus 7 10 to the power minus 6 coulomb. This is a charge outside. Okay. So of course, A is the correct answer. So you see here, I have used Gauss law. I have used conservation of charge. Okay. And I can even use principle of superposition. Let's say, for instance, I have solved the question. Okay, Alas. Now I'm just asking you extra questions. Now let's say, for instance, I ask you, what is the electric field here outside? What will you say? Of course, here I will use principle of superposition, and I will use also shell theorem. So basically, the electric field outside will be what? Will be just K Q net divided by R square. Now Q net here will be equal to what? Q net here will be equal to, by the way, this Q net is different from this Q net. Okay? This Q net, let me call it Q total. Okay? So Q total will be equal to the total charge, actually. Okay? So total charge is what? Total charge is just plus 12 10 to the power minus 6 minus 5 10 to the power minus 6. And this will give you plus 7 10 to the power minus 6. Okay. I'm using actually shell theorem. So the electric field outside is just K 7 10 to the power minus 6 divided by R square. Okay. So this charge will be like as located in the middle. The charge of my spherical conducting shell will be also like located at the middle. So outside I can use the shell fiber. Okay, good. Now, next question. I can ask you to draw the electric field lines inside here and outside here. You know how to do, so I will not talk about it. Okay, so let's go to the next problem. So this is what I did here already. Okay? And we solved it already. So let me go to the next problem. So read the problem carefully. So in this problem, we have a conducting spherical shell. Again, a conducting spherical shell. Okay? So we have a conducting spherical shell with inner radius A. So A is 5 centimeters and outer radius B, which is 7 centimeters. And it has a net charge. So Q net is equal to minus 3Q, okay, on this shell in gray here. Okay, the net charge is minus 3Q, as shown in the figure. Now I take a positive point charge plus Q and I place it here in the center of the shell. So plus Q is here. The question is very simple. Find the magnitude of the outer surface charge density. Okay. Assume that Q is 1.5 microcoulomb. Again, we already solved this. Okay. So if I have minus Q, plus Q, that means here all around I have a uniform density, uniform because it's in the middle. Okay, if it was not in the middle, so this is in my inner surface. In my inner surface, I will have just what? Minus Q, which is induced. Okay, good. Now, if I have induced minus Q in my inner surface because of the existence of this, that means here I have to add plus Q. Okay. Let's do it properly if you want. So here I will be using, let's say first I will be using this as we did before. This is my Gaussian sphere. It's passing inside my metal. It's a sphere, okay? It's not good looking, but it's a sphere. So this is my Gaussian surface. Let me apply what? Gauss law, integral over this Gauss surface, which is a sphere of E dot dA is equal to charge enclosed divided by epsilon naught. But again, the electric field here inside my conducting spherical shell is 0. So this is 0. So this integral is 0. That means charge enclosed should be 0. Now charge enclosed will be plus Q plus Q inside. Q inside, by Q inside, I mean the charge in the inner surface of my conducting spherical shell. And this should be 0. So that means charge inside, Q inside is just minus Q, as we said before and as we know. So I have plus Q here all around, and this is induced, by the way. This is induced net charge at the surface, at the inner surface. Okay, so I have minus Q distributed uniformly around my inner surface, uniformly because plus Q is in the middle here. If plus Q was here, of course, here I will be having more negative and here less negative. Okay? But overall, on my inner surface, the total charge is just minus Q. Now, second thing, I want the outer surface now, because that's what I want. I want the magnitude of the surface charge density on the outer surface. What should I do? Easy. I know that Q on my shell, Q net is minus 3 Q, and this is a constant. And this means even after I induce some charge in the inner surface, I have Q inside plus Q on my outer surface. I mean, Q inside, by Q inside, I mean Q in my inner surface plus Q on my outer surface is still equal to minus 3Q. That means Q on my outer surface is just minus 3Q minus Q inside. But Q inside is minus Q. So basically I have minus 3Q plus Q, which gives me minus 2Q. And this is my charge on the outer surface. So here on the outer surface, I will have a total charge of minus 2Q. Okay, good. Now the question is the magnitude of the surface charge density. Well, easy. If I have on my outer surface, so sigma out the surface is just total charge, which is minus 2Q, divided by total surface of my outer surface, which is 4 pi r outer square. By the way, r outer here is called B. Okay. So it will be minus 2Q. Q is 1.5 10 to the power minus 6 Coulomb divided by 4 pi B square, and B is 0.07 square. And you calculate it and you will get this number. So this is my surface charge density on the outer surface. And this is exactly what I did here. Okay. Charge outer surface divided by surface of my outer surface, and this gives me this number. Now, what is the magnitude of the surface charge density on my inner surface? So sigma inner, it will be just charge inner, Q inner, or Q inside. By inside, I mean Q inner on the inner surface, divided by 4 pi a square, because this is the surface of my inner sphere, of my inner surface. Good. So Q inside is just minus Q divided by 4 pi a square, and A is 0.05 square, and you calculate it. Okay, is it clear? Great. Now, what will be the electric field? I tell you now, calculate the electric field outside here, calculate the electric field inside the hollow sphere, and calculate the electric field here. Okay. Let me say that again. So this is an extra question. Now the question is calculate the electric field here. Okay. When I'm here, calculate the electric field here and calculate the electric field here. Let's do it. So we are just applying what? Gauss law. So the electric field here, let me choose this as my Gaussian surface. So I know that integral of E dot dA is just charge enclosed divided by epsilon naught. I will apply it first to this Gaussian surface here. Second, I will apply it to the second Gaussian surface here. By the way, electric field here is just 0, so I don't need to do anything. And what the electric field here on my outside. So here, of course, charge enclosed will be just plus Q divided by epsilon. So basically E multiplied by 4 pi r square is just plus Q divided by epsilon. So inside, I just have K Q divided by r square. Okay. Inside here, the only thing that is exerting, that is creating an electric field is this plus Q. Okay. Because this is not creating anything inside shell ferrite. Now, when I'm outside now, I have to add the electric field created by this and the electric field created by the conducting shell. Okay. And you will see that the E outside, if I apply Gauss law, basically it will give me, here it will be divided by 4 pi epsilon naught r square. And here it will be charge enclosed. But what is charge enclosed? Charge enclosed will be plus Q. Okay. But also charge enclosed will be plus minus 3Q. Okay. This is what I call charge net charge, the total charge. Okay. The electric field outside will be just plus minus 2Q divided by 4 pi epsilon naught r square. Okay. Just by the Gauss law. Okay. So Gauss law should be very quick. Okay. And you do it properly and you get the right answer to get the electric field of a highly symmetric distribution of charge. Now, let's look at this problem here. And it's a very interesting problem. So the problem reads, the magnitude of the electric field at a distance 0.145 meters from the surface of a solid insulating sphere. This is very important. It's a solid insulating sphere with radius 0.355 meters is this. Assuming that the sphere's charge is uniformly distributed, find the magnitude of the electric field inside the sphere at a distance 0.2 meters from the center. Let's draw a figure. Okay. So here I have a solid insulating sphere. Okay, solid insulating sphere. And I give you the radius. So this is my solid insulating sphere. Okay, let me just draw it this way. And I gave you the radius. The radius, I will call it capital R. And of course, capital R is 0.355 meters. Okay, you put everything in SI units. Okay, so it's a solid. So basically inside you have some material and it's insulating. Now the magnitude of the electric field at a distance 0.145 meters from the surface. So let's say this is the surface. And at this distance, let me write it down. This is H, let me call it H at an altitude or at a distance H, and H is 0.145 meters. The electric field here, E, is equal to 1,750 Newton per coulomb. Okay. So what can we do? First, we know that this electric field, well, this point is outside the surface. So it looks like shell Faraday. Okay. So this electric field here is just K, total charge of my sphere divided by R squared. But remember, the R here will be capital R plus H. The R is the distance from here to here. So R is capital R, which is the radius, plus the distance from the surface. Okay. So from here, I can get my Q. Q would be just the electric field multiplied by R squared, but R, as I said, is capital R plus H squared divided by K. So electric field 1750. Capital R is just what is capital R? 0.355 plus 0.145 square. Don't forget the square, okay? I take this square divided by K at H, K. Okay, K is 9, 10 to the power 9 SI units. So if you do that, you get your charge. The total charge is just 4.86, 10 to the power minus 8 coulomb. So the total charge is this. The total charge here is this number, okay? And it's uniformly distributed. So assuming that the sphere's charge, now I know the charge from the electric field by applying what? Shell Faraday. Or just by applying, of course, Gauss Law. Okay, Gauss Law here will give me integral of E dot dA. This is charge enclosed divided by epsilon naught. So E multiplied by 4 pi R square is charge enclosed, which is total charge of my solid insulating sphere divided by epsilon naught. That means E is just basically KQ divided by R square, as we know already. Okay. You can apply Gauss law now very well, I guess. So Q is this, I know Q. And it's uniformly distributed. It's okay, it's uniformly distributed. It's an insulating sphere. So inside I have charge and everything is uniformly distributed. So I can define what? A volume charge density. The volume charge density will be what? course, will be total charge divided by total volume, which is 4 pi r cubed divided by 3. So I can define what's the volume charge density. Okay? But I'll come back to that just in a second. Now, let's see the question now. The question is telling me to find the electric field inside this sphere at a distance 0.2 from the center. So basically, if I'm here and at this distance, basically 0.2, what is the electric field inside here? Okay. We already demonstrated this in class, by the way. The electric field inside an insulating sphere is what? Q divided by 4 pi epsilon naught r cubed multiplied by r. And we demonstrated this. Okay. But let's do it again. Let's demonstrate it again. Okay. To make sure that everybody understand what we are talking about. Of course, here by Q, I mean total Q. Okay, I mean this Q. So how to demonstrate that in a solid insulating sphere, the electric field is this? You apply Gauss law. Now R is here, so small r. Of course, here small r is 0.2 meters. And I use my Gaussian sphere, which is this. Let me apply Gauss law on this Gaussian sphere. I will have integral of E that dA will be Q enclosed divided by epsilon naught. Now, you can apply the formula directly, okay? Otherwise, you use Gauss law. Now, E is constant, so let me put it out. What is the area here? Of course, it will be 4 pi r squared. Now, what is charge enclosed? Well, charge enclosed is the charge inside this. So it will be the density, basically Q divided by the charge density, Q divided by 4 pi r cubed divided by 3, multiplied by the volume. The volume of this, inner sphere here, my Gaussian surface, which is just 4 pi divided by, multiplied by I cubed divided by 3. You see this 4 pi goes away, this way goes away, and don't forget to divide by epsilon naught. So you end up with E. And again, here r squared and this r cubed, because this goes away. So I'll end up with Q divided, which is the charge enclosed, divided by 4 pi epsilon naught multiplied by r cubed. Now I multiply by r. Okay. And this is what I get. And again, this is equal, we already demonstrated this in class as well. This is just what? Rho r divided by 3 epsilon naught. If you remember this. Okay. If I replace rho by this, you will get the same answer. Anyway. So the electric field that I want is this Q, which is 4.86 10 to the power minus 8 multiplied by R, which is 0.2 divided by 4 pi epsilon naught. Epsilon is 8.85 10 to the power minus 12 multiplied by R cube. Now what is R cube? R cube is 0.355 squared. Cubed. Okay. And you calculate this, how much do you get? You get this answer, 1,960 Newton per Coulomb. Okay. Is it clear? Good. So this is what I did here. Let me just show you again. From E outside, I get Q. And from Q, I just apply this formula, which is in your formula sheet. Okay. Which apply to a solid insulating sphere with a radius this. Okay. If you don't know what the formula, where is the formula? It's in your formula sheet. And in your formula sheet, it's written as this. Q 4 pi epsilon naught r cubed r. Okay. Which is just K Q R divided by R cube. And we demonstrated this in class. Okay. And another way to look at it, this is just rho R divided by 3 epsilon naught. rho being total Q divided by 4 pi r cube divided by, as we already talked about. So the rho is the volume charge density. Now here, let me just talk about a side note, and I want you to do it. Now, if I had, instead of having a solid insulating sphere, I had what? A solid insulating cylinder. Okay. And it has a radius r. Just on a side note. Okay, and it's very long, very long. And I ask you now, outside, what's the electric field outside? Electric field outside, you can get it pretty easily. Okay, I can use here a Gaussian cylinder, Gaussian surface, which is a cylinder, and I will apply Gauss law. So you will find that E multiplied by the lateral area. What's the lateral area? 2 pi r. So if this radius, I call it capital R, this distance to I call it small r. And here I'm looking at what's the electric field when r is bigger than capital R. So I have 2 pi r. Now, of course, don't forget to multiply by this. Let me call it the length L. And this is the area of the lateral surface, right, of the cylinder. And this will be equal to charge enclosed. Now, what is the charge enclosed? Of course, here the charge enclosed is this total charge, which is inside. Okay. So total charge, which is just Q, let me call it Q, divided by epsilon naught. And again, if I want to get Q, it depends. If I give you rho, you just multiply by V. Okay. Get my point? Okay. Good. If I give you the volume charge density, you multiply by the volume of the cylinder. Okay, good. So I'll have E multiplied by 2 pi RL is density, volume charge density, multiplied by the volume of the cylinder. What's the volume of the cylinder? It's pi r squared multiplied by L. Okay, this is this area here. Let me write it in a different. Okay. This area here, okay, multiplied by L. This is the volume of my cylinder and divided by epsilon naught. Okay. Again, here, be careful because the area that I'm looking is a capital because charge enclosed. So this R here is a capital R. Got it? Great. Now I will simplify by L first, and I will find that this is E. Of course, this pi and pi goes away. I will have rho R squared divided by 2 epsilon naught R. Okay. And this is my, let's say, my electric field outside. Okay. So let's rewrite this because I can rewrite this actually, right? So this, I can rewrite it as E is just Q divided by 2 pi epsilon naught L R. Okay. Okay. Now, if I say, what is Q divided by L? Q is the total charge divided by length. Well, this is my linear charge density. You remember in the first exercise? So E is just lambda divided by 2 pi epsilon naught R. And this is what we said in the first exercise. This is just 2K lambda divided by R. Do you agree with me? You see? Here I'm just defining, instead of talking about the linear charge density, I just talk about, instead of talking the volume charge density, I just talk about the linear charge density. Total charge divided by length. Because when I'm outside, and this is infinitely long, okay, you know, this looks like a wire to me. And you see, I'm finding the same relationship as if I had a wire and I'm looking at the electric field outside the wire. Okay, just to show you back, we had a problem like this earlier. Okay? Physics works. Okay, this Q divided by L is just lambda. Okay. Good. Now, what about inside? Get me the electric field inside. Here. What do you think? Now, when R, so this is, all this is R when R is bigger than R. Now, what happens when R is smaller than capital R? Well, I can come back here. Now here, this capital R square will be R actually. So let me write it down. If I apply Gauss law on this, cylindrical Gaussian sphere, I'll just get E multiplied by 2 pi R L, and this will be equal to what? Rho pi R square. Now, you see, because I'm inside, I have to take this R because I want the charge enclosed inside the spherical, inside the cylindrical Gaussian surface. Okay. Here, of course, the charge enclosed is inside this insulating solid cylinder. Okay, good. So here I will have this pi R square, I multiply by L, and I divide by epsilon naught. You see, this goes away. Of course, the L goes away, the pi goes away, this R goes away with this R. I have my electric field inside, which is just rho R divided by 2 epsilon naught. Okay, and it's different from a solid insulating sphere. Here I'm looking at a solid insulating cylinder. Okay. Okay, and this relationship is different. And again, this Q here, this rho here, I can write it as Q divided by the volume. But what's the volume? Pi R square multiplied by L multiplied by rho, and here divided by 2 epsilon. Okay, this is the rho divided by L here. So, okay. So there are many ways actually. So if I use this, I will just find that this is equal to Q. Okay. Let's look at it this way. Okay. So let's look at it this way. So this will be Q, because this R and this R goes away, and I will have Q divided by 2 pi epsilon L R. Okay, this is the electric field inside, and this is the same as this. It's the same thing. Okay, I just replace rho by its value. Okay. Yeah, I hope you see what I mean, and please do it. And there are some problems that will repeat this idea in a second. Oh yes, here it is. Now let's solve this problem. Yes, so talking about that, here we have exactly what I was talking about. So I have an infinitely long insulating solid rod, meaning insulating cylinder. Okay. It's infinitely long. Okay, and I give you the radius. And it carries a uniform volume density, charge density, a volume charge density rho. This is what I was talking about. Okay. So let me plot it. So I have a very long rod. So this is it. Oh, this is my, of course, radius R is 4.5 centimeters. And this is extremely long, extremely long. Okay. Going down. Good. And it has a volume charge density, uniform volume charge density rho. Of course, rho will be total charge of my rod divided by the volume of the rod. Okay. Now, what is the volume of the rod? It's a cylinder. So it's this area multiplied by this length. Let me call it L, not H, or length or height if you want. So V will be just pi R square multiplied by the length. Okay, which is this. Good. And it's insulating. Okay. So if I charge it, of course, this charge is all around the place inside. If it was a metal, of course, the charge will be only at the surface. Okay, so the electric field inside will be 0. Okay, but here it's a solid insulating cylinder or rod, same thing. Okay, good. So the question is, if the magnitude of the electric field at the surface of the rod, meaning here, is 1.6 10 to the power 4 Newton per Coulomb, find the magnitude of the volume of the charge density of the rod. So we will be applying Gauss law. Let's apply Gauss law. So since the electric field I'm looking at just right outside, so my Gaussian surface will be right outside here. And of course, it will be a cylinder. It has to respect. So this is my Gaussian surface. So if I use integral of E dot dA over this closed Gaussian surface, which is a cylinder, is just Q enclosed divided by epsilon naught. Of course, A is constant. It's pointing, let's say, outward. dA is outward, so E can get out. dA will be just, the lateral area, because of course here and here, dA is like this, so the flux is 0. So only the lateral area will participate in my total flux. So what is the lateral area? It's just 2 pi r multiplied by what? Multiplied by L. And this is equal to charge enclosed. Now we need to get the charge enclosed. So what's the charge enclosed? It will be just the density times the volume enclosed. What is the volume enclosed? Is the volume of the cylinder, the Gaussian cylinder. So what's the volume of the Gaussian cylinder? Of course, it's pi r square multiplied by L, and this divided by epsilon naught. Of course, L simplifies. What else? This pi and this pi simplifies. What else? This r and this r square goes away. So I end up with the electric field, as we already demonstrated, by the way, before. The electric field is just rho r divided by 2 epsilon naught. And I know that the electric field, and by the way, the r here is equal to capital R, because I'm just looking at the radius, so r is equal to capital R. By capital R, I mean the radius of the cylinder, which is 4.5 centimeters. Okay. So this is 1.6 10 to the power 4. I don't know rho. I know the R. R is 0.045 meters. To epsilon naught is 8.85 10 to the power minus 12. So my only unknown is rho. So let's get rho. Of course, rho is 2 epsilon naught E divided by radius. And I use it. What do I get? 6.3 10 to the power minus 6 coulomb per meter cube. Is it clear? Okay, good. So here I want this rho, okay? Sometimes people use different things. So here, for instance, here, what I did is my charge enclosed. I just said, well, charge enclosed is equal to what? Charge enclosed is my volume charge density, rho multiplied by V. Okay? Just use this. Charge enclosed. This Q is rho multiplied by V. Yeah, I know V. Rho is what I want, and I get it. Some people will choose a different way. They will say that charge enclosed, Q enclosed, is lambda multiplied by L. This is as we said before. If I consider this rod to be very, 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 very long, I can define a linear charge density. And in that case, the linear charge density would be total charge divided by the length being this. Okay. But this is also equal to what? Rho V, which is also equal. Another student will say, oh, I want to define the surface charge density. So he will say surface charge density multiplied by area. But here it will be which area? Of course, the lateral area. Okay, the lateral area is just 2 pi r L, as we said before. Okay. So you can define this type of relationship. Let me talk about it. And you see the big picture. I'll say lambda multiplied by L. This is rho multiplied by V. And what is V? We already talked about it. Pi r square multiplied by L. And this is equal to sigma multiplied by area, which is 2 pi r L. So these are the relationships that I have actually. Okay. In some problems, I can ask you what is lambda. In some problems, I can ask you what is rho. In some problems, I can ask you what is sigma, depending on what I'm looking at. If I consider that my cylinder is very long, and I give you lambda, and I give you this L, well, you know that, of course, my total charge is lambda L. Okay. Instead of that, if I give you the, the surface charge density sigma, you know that I have to multiply by the area, the lateral area, which is here, to get the total charge enclosed. If in another hand, for instance, in this problem, I gave you rho, or rho is what I want, you have to calculate, you have to multiply it by the total volume of the cylinder. Okay. So write down this relationship. It's very important. For a cylinder, I can apply it to a cylinder, I can apply it to a sphere, etc., etc. Yeah, good. Of course, a sphere will be very difficult because I cannot define this. Yeah. But in a sphere, I can define this and this, rho and sigma. But there is no L because L is not a symmetry, a symmetry axis, let's say. It does not go throughout. It's not very long. You get my point? Okay, let me stop here. Those who are interested will see more problems in this type of things. So actually, this is what I did here, okay? First, here, you see, this guy, he wants to use the formula. In this here, he wants to use the formula. It's infinitely long rod. We can look at it as a charge line. And he used the formula for charge line, and this is it. Okay. This is the formula for a charge line, the electric field, and then he get the lambda. And lambda, of course, is in coulomb per meter. And then he said, well, lambda is Q divided by L. And rho is, Q divided by V. Okay, so it's the same Q. This Q and the Q are the same. So I can define this relationship as I told you before. You remember? Q is rho V and V is pi r square L, which is lambda L. Okay, if you use these two, gentlemen, you get rid of the L. You'll find that rho is just lambda divided by pi r square. Okay, this is what he used here. Okay, and then he uses lambda, pi r square, and he get it. Okay. Another one will tell you, no, I don't want rho, I want sigma, and you know that better. This is sigma multiplied by the area, but by area I mean the lateral area. So 2 pi r L. Okay, the L also goes away. So I can say that basically, sigma is just lambda divided by 2 pi r. Okay. You get my point? Okay, good. Now also you can write a relationship between rho, pi r square L, and sigma, which is sigma 2 pi r L. Of course, the r L goes away, the pi goes away, this r and this r goes away. So you end up with rho just 2 sigma divided by r. Okay, so I have 2 sigma divided by this r, okay? Which is another relationship. Okay? All depend how you want to solve it, okay? And what the problem is guiding me towards what. Next, same type of problem, okay? An infinitely long non-conducting cylinder has this uniform charge density. And now I give you a volume charge density. And I give you the radius of the cylinder. Now, what is the magnitude of the electric field? 6.5, from the axis of the cylinder, meaning inside. I want rho inside. You use Gauss law. Okay, when you use Gauss law, this is what you get. Now here you have to tell it clearly. So you have epsilon naught multiplied by E. Okay, so you will have E multiplied by the Gaussian sphere. I mean the area of the Gaussian, this area, the lateral area. We already talked about it, okay? 2 pi R multiplied by H, or let me call it L, because I have been calling it L so far. And this will be equal to charge enclosed. Now what is charge enclosed? Well, it will be, of course, density multiplied by volume enclosed divided by epsilon naught. Okay, now what is a volume enclosed? I can get the volume enclosed. It's pi R square multiplied by L. So I end up with E 2 pi RL is rho pi R square L divided by epsilon naught. I simplify by L. And of course I simplify by pi. This R goes away and I get the same result that I told you before, rho R divided by 2 epsilon. Okay, good. So I know R is inside, this is inside. Okay, I know this, I can calculate the electric field and I find this. We already talked about this, right? Now what about outside? Well, outside it will just behave like what? Like a rod. Okay, and you can calculate it. Outside, basically, because this is infinite, I will just find that the electric field outside, this is electric field inside. Now outside, when R is bigger than R, I will have LE, which is just 2K lambda divided by R. But again, this lambda here, how do I need to define it? It's total charge divided by L. Okay. So you can say also, you know, this total charge is just rho multiplied by V, which is pi R square multiplied by L divided by L. Okay, so this lambda here, okay, so the electric field outside is just 2K lambda. I will replace it by what? This L goes away. I will replace it by rho pi R square. Okay, now I have to divide also here by epsilon naught. Did I make a mistake somewhere? Oh, yes, that's correct. So I made a mistake here. Okay. But you get my point, right? Okay, let me, I will not do this, but this is true. Now you can say that basically lambda is equal to what? Okay. As we said it before, Q, which is lambda L, is rho pi R square L. L goes away. That means lambda is rho pi R square. Okay. Okay. So here, of course, I will have rho pi R square. Okay. Anyway, you get my point. Now solve until this becomes so logical to you, so clear in your head that you will solve it in a fraction of a second. Okay. Now I will solve the last final type of problems that are very important. Okay. So this problem here, you see, it looks like this problem. Well, this problem we already solved it, so you don't need, you can look at it by yourself when you solve it. And we can solve this problem as well if you want. Okay. So I will end up with these two types of problems. I will start by this one and this one, and then I stop here. The rest I will let you solve them. So this problem, I want you to solve it. It's very interesting and very interesting. So look at it and solve it. The solution is given, and you are using all these different things that I told you already. And it's a very interesting problem. And you will solve also this problem. It's a very interesting problem, but I don't want to spend time on it. The solution is given, understand it. If you have questions, stay to come to my office hours. I cannot solve all the rest, okay? So please solve the rest of the problems, solve all what you can, and understand is more important than memorizing. So understand what's going on, how to apply Gauss law, what happens if I have this type of, you know, spherical conducting shell, or I have an insulating, you know, solid cylinder, etc., etc. So for the time which is remaining, I will solve these two problems and we will stop here because I'm tired. So now let's look at this type of problem, which is also very important. Okay, this type of problem are very important. So we have two large, very large, okay, non-conducting plastic sheets. Each has a thickness of 10 centimeters. So they carry uniform charge densities, sigma 1, sigma 2, sigma 3, and sigma 4. You see here I have sigma 1, here I have sigma 2, here I have sigma 3, and here I have sigma 4, as shown in the figure below, as you can see. These surface charge densities have value. Sigma 1 is negative, okay? Sigma 2 is positive. Sigma 3 is positive, and sigma 4 is negative. The question is very simple. Find the magnitude of the ratio EA divided by EB of the electric field at point A and B that are far from the, not far, okay, from the edges of this sheet. Basically, I have here A and B here. So now first I need to find what the electric field here at A and what the electric field here at B. Let's find them. First, electric field at A. Of course, here, you know, I have a non-conducting sheet, right? And if I have a non-conducting sheet, what is the electric field? Electric field is just sigma divided by 2 epsilon naught. So electric field here at A will have, you know, it will be E1, basically electric field created by this side or this surface of charge sigma 1. So let me put vectors. Plus electric field due to this side here, sigma 2, plus electric field due to sigma 3, plus electric field due to sigma 4. Let me take this as a positive x-axis. And I project now along x. So EA in magnitude will be what? E1, of course, here, E1, sigma 1 is negative. So E1 will be pointing in the negative direction. Do you agree with me? Okay, it will be pointing towards, of course, the negative charge. I mean the negative surface, which is sigma 1 here. So it will be minus E1. Do you agree with that? E2 is positive, right? So since it's positive, that means E2 will be pointing away. So E2 will be pointing away. Okay? So that means minus E2 as well. E3 at A. I'm talking about at A, okay? Now E3, of course, this is positive. Sigma 3 is positive, so E3 will be pointing away. So minus E3. Now E4 is negative. So this is E3. E4, sorry, sigma 4 is negative. That means E4 will be pointing towards. So plus E4. Okay. So this will give me minus absolute value of sigma 1. Okay. Minus absolute value of sigma 1 divided by 2 epsilon naught minus absolute value of sigma 2 divided by 2 epsilon naught minus absolute value of sigma 3 divided by 2 epsilon naught plus absolute value of sigma 4 divided by 2 epsilon naught. Okay, because this is a magnitude. The sign is already taken into account here. So I will have what? 1 divided by 2 sigma naught minus absolute value. So I will have minus 3.5. And here I will have minus 3. And here I will have minus 1.5. And here I will have plus 2.5. So this is what? Of course, microcoulomb. So 10 to the power minus 6. This is what? Well, this is minus 6.5. So this is what? This is plus 1. So overall, I will have minus 5.5 and to the power minus 6 divided by 2 sigma naught. This is EA. And of course, I want to take magnitude, so I take absolute value of this later. Now at B, I will do the same. Now at B, say B is here, sigma 1. Of course, sigma 1 is negative, so it will be going towards this direction. Sigma 2 here, positive, so away, right? So this is E1. So E2 will be pointing in this direction because sigma 2 is positive. Sigma 3 is positive, so it will be pointing away, E3. And finally, sigma 4 is negative, so it will be pointing towards. So E4, or no, EB will be what? So let me put so I'll have minus E1 plus E2 plus E3 plus E4. I'll have 1 divided by 2 epsilon naught minus absolute value of sigma 1 plus absolute value of sigma 2 plus absolute value of sigma 3 plus absolute value of sigma 4. So this will give me what? Minus absolute value of sigma 1, 3.5, plus absolute value of sigma 2, 3, plus absolute value of sigma 3. What is sigma 3? 1.5. Absolute value of sigma 4, 2.5. Did I make a mistake somewhere? It's possible. Anyway, so here, this will give you minus 0.5, and you add it to this, so this will give you 1 and 3.5. So EB, I find 3.5 10 to the power minus 6 divided by 2 epsilon naught. If I take the ratio, of course, EA divided by EB, absolute value, EA divided by EB, I just find 5.5 divided by 3.5. And this will give you what? 1.6. 5.5 divided by 3.5. This gives you 1.6, okay, as expected. Good? Okay, good. Now that's what we did, and okay, have a look at it, and we solve it. Okay, good. This, I have just used the principle of superposition. Principle of superposition. Okay, good. Now finally, let's solve this problem here. Okay, it's an excellent problem. I want you to solve it and know what it is about. So here I have plates A and B. So two vertical insulating planes, charge planes A and B with negligible thickness are parallel. So the magnitude of the electric field in region 1 here is 3 sigma divided by 2 epsilon naught. Okay. While the magnitude field in region 3, which is here, is also 3 sigma divided by 2 epsilon naught, where sigma is a positive surface charge density. And the magnitude of electric field in region 2, which is here, is just sigma divided by 2 epsilon naught. The figure 5 shows the direction of electric field. Here, of course, the electric field, of course, electric field is pointing in the negative direction. Here it's pointing in the positive direction, and here it's pointing in the positive direction. The question is, determine the surface charge density on planes A and B respectively. So the same problem, I can use, A, B, C plate. I can use as many plates as I want. Okay. I have to use principle of superposition. Okay. Good. Now, first thing first, let's analyze the physics here. You see here something which is extremely important. In the middle here, as I told you before, and we solved a problem like this before, in the middle here, I have electric field which is smaller than electric field here. So what do I have here? Here I have 3 sigma divided by 2 epsilon naught. Here I have 3 sigma divided by 2 epsilon naught. And here I have sigma divided by 2 epsilon naught. So the electric field in the middle is smaller actually. That means that A and B have the same sign, okay? If they had opposite sign, the electric field in the middle will be larger because they will be adding up. One will be, radially divergent. The other one will be radially, converging. But they will both be in the same direction, so the electric field will add up. Okay, if one was positive, A was positive, let's say, and B was negative. Okay, but that's not the case. The electric field here in the middle, the net electric field is smaller than the electric field outside. That means my 2 charge, my sigma A basically, and sigma B are both positive in this case. Not only positive, but I know also which one is bigger. Of course, sigma A has to be bigger than sigma B. Now you know why. Okay, the electric field is always pointing towards lower potentials, electric potential. Okay. Anyway, so I know that sigma A and sigma B should be positive, number 1, such that here in the middle, well, if sigma A is positive, so here in the middle, of course, the electric field is pointing away. So this is EA. If sigma B is positive, EB will be in opposite direction here, EB. Okay, good. Now let's look at the region free. If A is positive, of course, sigma A is in the positive direction, and sigma B, EB is also in the positive direction. Okay, so here in the region 2, I will have what? Of course, what's the electric? So here, if I have sigma A, the electric field will be, so here the net electric field, let me say E net is EA plus EB. And E net is what? I already know it, it's sigma divided by 2 epsilon naught, because it's given by the problem here. The region 2, the E net is this. And this is sigma A divided by 2 epsilon naught. Be careful here, because I made a mistake. So here it's minus, of course, okay? Because EB is pointing in the negative direction. So this is a minus. So minus sigma B divided by 2 epsilon naught. And I have my first equation, 2 unknown. So my first equation is just sigma, is basically sigma A minus sigma B. First equation, 2 unknowns. Now this comes from region 2. Now in region 3, I can say that EA plus EB is E net, which is just 3 times sigma divided by 2 epsilon naught. So that means sigma A divided by 2 epsilon naught plus sigma B divided by 2 epsilon naught is equal to 3 sigma divided by 2 epsilon naught. I simplify by epsilon naught and I get my second equation. Sigma A plus sigma B is equal to 3 times sigma. So I solve these 2 equations, a system of 2 equations, and I'll get that sigma A is 2 sigma and sigma B is sigma. And this makes sense, okay? If sigma A is 2 sigma, sigma B is sigma, the net electric field here will be smaller and it will be pointing in the positive direction. And the net electric field outside will be larger, okay? Good. Okay, so this problem, we already solved it and I want you to solve it again. So solve as much as you can, okay? This is an interesting problem. This is also a very interesting problem. You go through them and you solve them. Solve as much as you can and understand. Okay? Understanding beats, of course, memorizing. So let's stop here. It took me maybe 2 hours, but I think this was a very important recitation. That's why I recorded it. So make good use of it, inshallah. Okay? Assalamu alaikum.